All right, hi everyone. So this is going to be our last round of notes that we're going to have for this school year, which I'm sure makes you excited. Makes me a little sad, but we'll get on with it. So you've already been looking at chemical reactions in Pol-Goal form, right? So we looked at types of chemical reactions. We had some intro activities. Now we're just going to work through the notes, being able to identify reactions, but also balancing them. So the notes go a little bit out of order. We're going to do balancing first and then types of reactions second, but it's okay. It'll all be there. When we look at what a chemical reaction is, we are looking at one or more reactants changing into one or more products. And we are looking at the atoms simply being rearranged. And so, if you have hydrogen to start, you have to have hydrogen somehow in the end. It just might be in a different form. Okay. And our reactions take place all of the time. A lot of things we do in everyday life are chemical reactions. Anytime we cook or bake, it's a chemical reaction. And then combustion reactions as well. So anytime you light a candle or, like a lighter or light a match, we have a combustion reaction. So some basic information. When we're looking at a chemical reaction, on the left-hand side of the arrow, this is our reactant. So these are going to be your compounds that actually do your reacting, meaning if I went to the lab table in our classroom and I put two bottles of chemicals in front of you, those are your reactants. So nothing has happened yet. Then on the right are going to be the products. These are going to be the things you make, right? So I mix two things together and voila, something happens. That voila is a product. It could be the formation of a gas, meaning our reaction could bubble. We could get a precipitate. All of a sudden, a different color falls out of the reaction. And then we have separating them an arrow. Okay, the arrow means a couple things: yields, produces, changes into, but it shows you the direction the reaction takes place, meaning I start with my reactants and I end with my products. Okay? And so we have a couple ways we can do chemical equations. We can have word equations. So this is an example of a word equation here. Iron reacts with oxygen to form iron 3 oxide. So it's a word equation because literally everything's written out with words. Now, iron and oxygen would be our two reactants, right? Reacts with, so there'd be a plus sign there. To form means that's where I'd find my arrow, and then iron 3 oxide would be my product, right? Here is it with chemical formulas. So here's my solid iron reacting with my gaseous oxygen to form my solid iron 3 oxide. And believe it or not, this is a reaction that many of us have seen before because iron 3 oxide is actually rust. Okay. Um, in our reaction, okay, we just saw this in our example, we have some things that indicate physical state. So S is just going to stand for solid, L for liquid, G for gas, so we're familiar with these three, and then AQ is going to be aqueous, which simply means dissolved in water. Okay, so we can see the states indicated here: solid iron, gaseous oxygen, and solid iron 3 oxide. Okay, so I have some examples of reactions that we would have looked at in class. So I found some YouTube videos of them. So we have solid magnesium reacting with gaseous oxygen to make magnesium oxide. So you can watch these YouTube videos at your leisure. Okay, we have solid copper reacting with silver nitrate. So it's an aqueous solution. We put the solid copper in there, and we actually do form solid silver in aqueous copper 2 nitrate. So the solid silver we can see form on that wire. You can see the kind of clumps of silver, and it will fall off if you hit it. And the solution itself goes from clear to blue, and the blue solution is that copper solution. Okay. Here we have our very famous precipitation reaction. We're making solid iron to iodide, and it's a bright yellow solid. So you can watch this video. This actually, the video extends. It's called this golden experiment, okay, the golden flake experiment. So the reaction that we would have watched in class happens in about the first 45 seconds, but if you keep watching, they'll show you how to make this kind of like gold glitter solution. Okay, and then last but not least, we have solid sodium sulfide with hydrochloric acid is going to produce a gas, right, and aqueous sodium chloride. So when we look at driving forces of a reaction, there are four things that we can have happen that drive that reaction to take place, meaning it'll cause that reaction to take place. So the first one is going to be to form a gas. Okay, so if I can form carbon dioxide, if I can form gaseous oxygen, gaseous hydrogen, Okay, that's a driving force of reaction. The second one is going to be to form water. Okay. The third one is going to be the transfer of electrons. We're not going to see many of these reactions, even in our examples. And the fourth one is to form a precipitate. And so this is the one that normally in class we spend the most time on because your lab final would have been based on it. Okay. For classifying reactions, we have 5 types of reactions, and you saw them in your POGIL packet. The first is a combination reaction. So we're literally going to take multiple reactants, and we're going to combine them to make one product. So we can see in this basic equation that we have 2 things on the left, and they're just combining. I could have 45 things on the left, and as long as they combine to make one singular product, combination reaction, and here's an example, the magnesium oxide reaction we previously watched. Okay. Our second type of reaction is going to be a decomposition reaction. So it's literally the opposite of combination. Here we're going to start with one reactant and it's going to break down into 2, 3, or 45 products. We have solid mercury 2 oxide is going to make liquid mercury and gaseous oxygen. That's going to be an example. Our third type is a single replacement reaction. And here we're going to have a singular element replacing another element in the compound. So we look at our example. We start off in the reactants with solid zinc and then a copper solution, a copper 2 nitrate solution. And in our products, now look that the copper is by itself and the zinc is in solution. So the copper and zinc have literally flipped spots with one another. Okay, so that would be a single replacement reaction. The fourth type of reaction is a double replacement. So now it's kind of like single replacement, but notice there's no singular element. We just have 2 compounds. So what we're going to do is we're going to take the first element in each compound, the metals, and they're just going to flip spots with one another. So sodium and cadmium flip spots. Sodium was previously with the sulfur, now cadmium is. Cadmium was previously with the nitrate, now sodium is. Okay, so they literally just flip-flopped with one another. And last but not least are combustion reactions. These are the hardest ones to balance, we're going to see, but they're actually the easiest to identify because the basic reaction has something plus gaseous oxygen makes carbon dioxide and water vapor. So these 3 things, the oxygen and the 2 products are the same every single time. The only thing that's going to change is that whatever we're combusting. Okay, so those are our 5 types of reactions. Combination, multiple things come together to make one. Decomposition, one thing breaks down into multiple. Single replacement, we have a singular element, flipping spots with the metal in a compound. Sometimes it can be the non-metal. We have a double replacement, 2 compounds flip their metal ions, and then combustion reaction. Now for balancing. The most important thing to remember when we balance chemical equations is that atoms are neither created nor destroyed. Okay, they're simply just rearranged. So if I have 25 oxygens on my reactant side, I have to have 25 oxygens on my product side. And that's actually why we balance equations. Okay, so the first thing I always do is if I get an equation, if I'm given one, I just automatically check to see if it's balanced, because if it's not, that's going to be my first step every single time. Okay? And the other important point is that when you balance, you cannot change your identity of your compound. So this is calcium carbonate, and notice that the subscript here is a 3, right? There have to be 3 oxygens in that carbonate. If I need to say 6 oxygens, I can't just change that number to a 6 because that changes the identity of my compound. It's not calcium carbonate anymore. So what I'm going to do is I'm going to put coefficients. I'm going to put numbers in front of my compounds to change it. And yes, it does change everything in the compound, and we'll see that kind of cascading effect. But it will be fine. Okay, so here are going to be our steps, and I'm going to walk through a couple with you. We're going to count each element on each side first and make a little table for ourselves. Okay? And then we're going to go polyatomics. We're not going to see many of those because we're not going to get into really hard balancing. Then we'll do our metals, our non-metals, and then lastly, hydrogen and oxygen. They're usually the trickiest to balance. So we usually wait till the end because we kind of cross our fingers that they get balanced when we do everything else. Okay, and then we'll reduce our coefficients if possible. Okay, so for example, here is the reaction, the formation of water. We have gaseous hydrogen plus gaseous oxygen makes liquid water. So I'm going to follow my steps. I'm going to count each element on each side. So my number of hydrogens and my number of oxygens. On the left, I have 2 hydrogens right here. On the right, I also have 2 hydrogens. Okay? On the left, how many oxygens do I have? So I look and I see that I have 2. I go to the right and I see that I actually only have 1. So the reaction is almost balanced, except for this tricky little oxygen. Now, when I go to balance my equation, again, I can only put numbers in front of my compounds. And if I put a number here, let's say I put a 16, the 16 is going to apply to both things in the compound and it actually multiplies out. So if I need 2 oxygens here, sometimes my thought would be to put a 1, right? 1 plus 1 equals 2. But if I put a 1 here, it's going to be 1 times the 1. And so I'm going to end up with 1. So what I'm going to do is I'm actually going to put a 2 in front of that compound. 2 times that 1 is going to give me 2. But then it's also going to multiply out by this element. So 2 times 2 is going to give me 4. So here are my new numbers on my right. So in balancing my oxygen, I did unbalance my hydrogen, but it's okay. I can easily fix it. So if I look at this side, what number could I put in front of this to get 4 hydrogens? And I can see that I put a 2 there, and that gives me 4. So now I have 4 hydrogens on the left and the right, 2 oxygens on the left and the right, and my reaction is balanced. Okay, so that was my first example. Here's my next example. So again, I'm going to chart it out. I'm going to count my potassiums, my hydrogens, and my oxygens, and notice I keep the elements in the same order on both sides, even if they're not in that order, because it's easiest to kind of compare. So on the left, I have 1 potassium. On the right, also 1 potassium. Okay? On the left, I have 2 hydrogens. On the right, I actually have 3 hydrogens. I have 2 here and 1 here. That does make it a little tricky. On the left, I have 1 oxygen. And on the right, I have 1 oxygen. So we can see, again, the only thing not balanced is that stinking hydrogen. Just note, to balance it, I am going to have to unbalance a couple things. So this one, when I go to do this problem, my first thought is actually to get my hydrogens to an even number because nothing I put in front of this on the left is going to give me an odd number. So I have to get rid of this odd number. So what I'm going to do is I'm just going to test it. If we were in class, we'd do this with pencils, so we could erase it. What I'm going to do is I'm going to put a 2 in front of this compound, and I'm going to multiply everything out. So this is now going to give me 2 potassiums. It's going to give me 2 oxygens, and then it's going to give me 2 hydrogens here that I have to add to these 2, so I get 4. So here's my counting on the right, and notice it's literally double. So what I'm going to do is I'm just going to fix it over here. So to get 2 potassiums, I'm going to put a 2 in front of that. So I get 2 there. And to double this, I'm going to put a 2 in front of this. And then I get 4 and 2. So this is balanced. And note, it's 2, 2, 1, 2. So they're not all 2s. It may seem like it, but they're not. This has a coefficient of a 1, so it's already as reduced as it can go. Okay, let's try to do one more. Okay, so I'm going to count it out really quick. Here's my chart. So hopefully you can see where all these numbers came from. I'm going to balance out my nitrogens first, okay, because my nitrogen is not oxygen or hydrogen. So I want to get 2, so I'm going to put a 2 in front of this, and I'm going to multiply everything out. So there's my 2 nitrogens and my 2 oxygens. Okay. Now, which one do I want to balance next? I think I'm going to go with my oxygen. So I'm going to put a 2 in front of water on the right, and I'm going to recount out. Now I have 2 oxygens and 4 hydrogens. So I can then put a 2 in front of that compound and get my 4. Okay, so again, this ended up being 2, 2, 1, 2, just like the last one. Okay, I can give you one more example here. This one's a slightly easier one. Okay, put a 2 there, recount, put a 2 in front of lithium, and I'm done. Okay, so those are my examples of balancing. So hopefully that made sense. If you have any questions, please come see me again. These are our last notes. So everything else you just have are just practice with this. All right. I do miss you guys a lot. I wish I could see you guys again, but maybe I'll see you in office hours. Bye, guys.